We call it the Boötes Void, and for decades we thought it was just empty space doing what empty space does. But recently, we detected something inside, something that moves, something that pulses with energy, something that, according to every law of physics, cannot exist in a place that empty. If you enjoy unraveling cosmic mysteries with us, hit that like button and subscribe. What we found hiding in the void changes everything. Prepare yourselves. We begin. Picture this. 1981. Robert Kirshner and his team are mapping galaxy positions for what should be routine work. They expect to see galaxies scattered everywhere, the way stars fill the night sky. Instead, their instruments show a gap, not a small gap, a region where galaxies just stop existing. They check their equipment 3 times. The readings stay the same. They expand their survey outward, following the edges of this emptiness. It keeps going and going, until they realize they are staring at something 330 million light-years wide. To understand that scale, imagine our entire galaxy is the size of a quarter. You would need to line up 33 million quarters, edge to edge, to cross this void. Light itself, traveling at 671 million miles per hour, needs 330 million years to make the journey from one side to the other. The team names it the Boötes Void, after the constellation where it hides. They calculate how many galaxies should occupy this volume of space, based on the average cosmic density. The answer comes back, around 2,000 galaxies minimum. They count what actually exists inside. 60 galaxies. 60. That means 97% of the galaxies that should be there have vanished, or never formed in the first place. The discovery sends shockwaves through astronomy because voids this empty are not supposed to exist according to our models of cosmic evolution. Matter should be distributed more evenly throughout space. Something carved out this region and left almost nothing behind. But here is where the story takes a darker turn. Those 60 galaxies that remain are not randomly scattered. They cluster along the void's edges in thin chains, like they are fleeing from something at the center, like they know better than to venture too deep inside. When Kirshner publishes his findings, other astronomers rush to point their instruments at this region. Every telescope confirms the same thing, a sphere of almost perfect emptiness hanging in space. Most scientists assume it is just an unusual statistical quirk, a cosmic accident. The universe occasionally rolls the dice and comes up with weird results. Except the void keeps revealing stranger properties. The few galaxies inside show unusual traits. Their light spectra look wrong. Their velocities do not match predictions. Something about the space itself seems different. And 40 years later, we detected energy signatures coming from deep within that emptiness. Patterns that repeat. Structures that should not form in a void. The question shifts from why is it empty to what exactly is hiding inside. Because empty space does not emit signals. Empty space does not organize itself into patterns. Whatever we found in there is doing something. And we need to understand what happens next before it is too late. Our current model of the universe works like a recipe. You start with the Big Bang, add dark matter and dark energy, sprinkle in regular matter, and let gravity do its work for 13.8 billion years. The result should be a cosmic web, filaments of galaxies connected like spider silk, with smaller voids scattered between them. The largest voids in this model should measure around 150 million light-years across, maybe 200 million in extreme cases. That is what the math predicts. That is what most of space looks like when we observe it. The Boötes Void measures 330 million light-years across. It doubles the maximum size our physics allows. This is not a small discrepancy. This is like predicting a human can grow 6 feet tall, and then finding someone who stands 12 feet high. The difference demands explanation. Here is why it matters. In the early universe, matter distributed almost evenly in all directions. Tiny quantum fluctuations created slightly denser and slightly emptier regions. Gravity pulled matter from emptier zones into denser ones. Over billions of years, this process carved out voids surrounded by walls of galaxies. But gravity works at a specific speed. It can only pull matter a certain distance in the time since the Big Bang. Run the calculations backward, and you find that creating a void this large requires either much more time than the universe has existed, or much stronger forces than gravity can provide. Neither option makes sense. The universe is not older than we measured. Gravity has not changed its strength, yet the void exists anyway, sitting there like a hole in reality that violates the rules. Some physicists suggested dark energy expanded this region faster than normal. Dark energy pushes space apart, so maybe it concentrated in this zone and inflated the void beyond typical limits. The theory sounds reasonable until you check the math. Even with maximum dark energy concentration, you still cannot reach this size without breaking other cosmic constraints. Others propose this region started with much less matter than average, a statistical fluke on a massive scale. But the probability of that happening calculates to essentially zero. You would need to win the cosmic lottery billions of times in a row. The truth is, we have no standard explanation that fits. The void should not exist according to our best physics. Yet, every telescope that looks at this region confirms it does exist. Which means either our understanding of cosmic evolution is wrong, or something else happened here that we have not discovered yet. And recent observations lean heavily toward that second option, because voids are supposed to be passive. Empty regions do not do anything except exist. They certainly do not emit organized energy patterns. But the Boötes Void is doing exactly that, which suggests it is not just a void. It is something far stranger wearing a void's appearance. Stand outside on a clear night and look up. Every star you see belongs to our galaxy. Even the faintest pinprick of light sits within 100,000 light-years of Earth. That is our neighborhood, our local reality. Now, multiply that distance by 3,300. That is the width of the Boötes Void. It swallows 330 million light-years of space. To cross it, you would need to travel at light speed for longer than complex life has existed on Earth, multiple times over. Here is another way to grasp it. Take our Milky Way galaxy with its 200 billion stars. Place another galaxy just like it 50 million light-years away, then another, then another. Keep going until you have positioned 2,000 massive galaxies in a sphere. Now delete 97% of them. Leave only 60 scattered around the edges. That is what we are looking at. The void contains enough empty space to hold thousands of galaxy superclusters, regions where millions of galaxies should be gravitationally bound together, forming the largest structures in the cosmos. Instead, we find darkness, silence, a cosmic dead zone that stretches beyond human comprehension. Light from one edge of the void takes 330 million years to reach the other edge. When that light began its journey, the most complex life on Earth consisted of single-celled organisms, no plants, no animals, no humans. By the time the light completes its crossing, entire species have evolved and gone extinct multiple times over. This is not just big, this is functionally infinite from a human perspective. You could fit 75,000 Milky Way galaxies side by side across this emptiness. You could lose our entire local group of galaxies inside it and never find them again. The void could swallow every galaxy humans have ever observed through telescopes and still have room left over. And yet, despite this incomprehensible scale, astronomers mapped the entire structure in just a few years. How? Because emptiness has a signature. Where galaxies should create light, this region shows darkness. Where matter should bend space, the void leaves space flat. It stands out like a missing tooth in an otherwise complete smile. But size alone does not explain why scientists keep studying this region. Plenty of large structures exist in space. What makes the void terrifying is not how big it is what that size represents. The void shows us that our universe can create regions where the normal rules simply stop applying, where cosmic evolution fails to produce the expected results, where something fundamental breaks down. And if it happened once, creating this impossible emptiness, what stops it from happening again? What prevents other regions from developing the same properties? What if voids like this are spreading? The answer to that question came from an unexpected direction, from the 60 galaxies that refuse to leave. Gravity does not work alone in shaping the universe. It has an opponent, a force that pushes instead of pulls. We call it dark energy, and it makes up 68% of everything that exists. Here is how the battle plays out. In the early universe, matter distributed almost uniformly in all directions. Tiny variations in density appeared, no larger than 1 part in 100,000. In slightly denser regions, gravity won. It pulled nearby matter inward, creating the first stars and galaxies. These zones grew denser over time, but in slightly emptier regions, the opposite occurred. With less matter present, gravity weakened. Dark energy, which pushes uniformly everywhere, began dominating instead. It shoved the remaining matter outward, evacuating these zones even further. The emptier they became, the stronger dark energy's influence grew. This process created voids. Think of them as anti-galaxies, places where dark energy beat gravity in their cosmic tug-of-war. Matter fled these regions, piling up along the edges and forming the walls of galaxies we observe today. The interior became increasingly empty as time passed. Most voids grow slowly. They start small and expand over billions of years as dark energy pushes matter away. Their growth rate depends on their initial emptiness and the density of surrounding space. Run the simulations, and you get a predictable distribution. Lots of small voids, fewer medium voids, almost no large voids. The Boötes Void violates this distribution. It sits beyond the size range our models predict. Even accounting for maximum expansion rates and optimal starting conditions, you cannot grow a void this large in the time available, unless something else happened. Some cosmologists propose the void formed from a bubble collision in the first moments after the Big Bang. During cosmic inflation, space expanded faster than light for a brief instant. If two expanding bubbles collided and merged, they might create an underdense region that grew into an enormous void later. The theory has merit. Bubble collisions could explain the exceptional size, but it requires precise timing and positioning that seem unlikely, and it does not explain the other anomalies we detected. Other scientists suggest the void formed from primordial quantum fluctuations scaled up to cosmic size. Imagine a region where quantum uncertainty created slightly less matter than average. Over billions of years, that tiny difference amplified until it produced this massive emptiness. Again, possible, but the probability calculations come back unfavorable. Random chance almost never creates outliers this extreme. The truth is, we keep proposing theories because the standard explanation fails completely. Voids are supposed to be simple structures. Matter leaves, dark energy dominates, the region stays empty. Nothing complicated. Yet the Boötes Void refuses to behave simply. It formed too large. Its interior shows unexpected activity. The galaxies inside display bizarre properties. Everything about it suggests something beyond normal void formation occurred here. And when we detected those energy patterns last year, the debate shifted entirely. Because now we are not just asking how the void formed, we are asking what moved in after. Most voids contain some galaxies. A few dozen scattered through the interior. They form early in cosmic history before the void fully evacuates, or they wander in later from surrounding regions. Nothing unusual about their presence. The 60 galaxies inside the Boötes Void are not like that. They break multiple rules simultaneously. First, their positions. They avoid the void's center completely. Instead, they cluster along the edges in thin filaments, like beads on a string. This distribution makes no sense gravitationally. If they formed naturally inside the void, they should spread more evenly. If they fell in from outside, they should sink toward the center where gravitational potential is lowest. Instead, they stay near the walls, like they are being held there by something we cannot detect. Second, their ages. Spectroscopic analysis reveals these galaxies are old, very old. They contain ancient stars that formed when the universe was much younger. Most galaxies in voids are small and young, having formed recently from leftover gas. The Boötes galaxies look like mature elliptical galaxies that belong in dense clusters, not empty voids. How did old, massive galaxies end up in the emptiest region of observable space? Did they migrate here? Were they pushed? The motion patterns do not support simple migration. Something else placed them in these specific positions. Third, their velocities. Galaxies move through space at speeds determined by local gravitational fields. Measure a galaxy's motion, and you can infer the mass distribution around it. The Boötes galaxies move wrong. Their velocities suggest they feel gravitational forces from matter that is not there, matter we cannot see. You might think dark matter explains this. Dark matter fills most of space, providing invisible mass that affects galaxy motion. But voids specifically lack dark matter. That is part of what makes them voids. The dark matter evacuated along with regular matter. Yet the galaxies inside Boötes behave like dark matter surrounds them, like the void is not actually empty. Fourth, their light. Every galaxy emits radiation across multiple wavelengths. Visible light, radio waves, X-rays. The spectrum tells us about the galaxy's composition and activity. The Boötes galaxies show spectral anomalies. Specific wavelengths appear dimmer than expected. Others appear brighter. The pattern does not match any known galaxy type. Some astronomers propose the void's emptiness affects how light travels through it, altering what we observe. But light does not change properties just because it crosses empty space, unless the space itself has unusual properties. Which brings us to the most disturbing observation. The 60 galaxies are not randomly oriented. Their rotational axes point in similar directions, not perfectly aligned, but statistically improbable. Like they are all responding to the same external influence. Galaxies form from collapsing gas clouds that rotate randomly. Their orientations should show no pattern across large distances. Finding alignment suggests a force acted on all of them simultaneously. A force strong enough to influence their formation or alter their rotations afterward. We have no idea what that force could be. Nothing in standard physics operates on such scales. Yet the alignment exists in the data, confirmed by multiple independent surveys. The 60 galaxies are not just survivors in an empty void. They are markers, clues pointing towards something we have not discovered yet, something that organized them, something that keeps them in place. And recently, we found it starting to wake up. Galaxies age like living things. Young galaxies burn bright blue, filled with hot, massive stars that form rapidly from abundant gas. As they mature, the largest stars die off, leaving cooler, redder stars behind. The galaxy's light shifts toward longer wavelengths. Eventually, star formation slows or stops completely. The galaxy becomes a red, dead elliptical filled with ancient stars. This process takes billions of years. You can determine a galaxy's age by examining its light spectrum. Blue light means young stars forming now. Red light means old stars formed long ago. The ratio tells the story. The 60 galaxies in the Boötes Void shine predominantly red. Their spectra show populations of stars 10 to 12 billion years old. These galaxies finished forming stars billions of years ago and have been coasting through time ever since. They look like retirement homes for stars. Now, here is the problem. Galaxies like this form in dense environments. When you pack many galaxies close together in a cluster, their mutual gravity heats the surrounding gas to millions of degrees. This hot gas cannot cool down and collapse to form new stars. Star formation shuts off. The galaxies age rapidly and turn red. Voids have the opposite conditions: low density, cold gas, minimal interactions between galaxies. These conditions favor ongoing star formation, young, blue galaxies, not ancient red ones. So how did old elliptical galaxies end up inside the most empty region of space? The standard explanation suggests they formed elsewhere in dense clusters, then somehow migrated into the void. Galaxy migration happens. Gravitational interactions can fling galaxies across vast distances, but the math does not work. To reach the void's interior from any nearby cluster, these galaxies would need to travel 50 to 100 million light-years. At typical galaxy velocities, that journey takes several billion years. During that time, they would pass through regions with fresh gas. Star formation would reignite. They would not stay pure red. Yet they are pure red. No signs of recent star formation. No blue young stars mixed in. They aged in place, not during a long migration. Some scientists propose these galaxies formed inside the void when it was younger and denser. Before dark energy evacuated the region, enough matter existed to create these mature galaxies. Then the void expanded around them, leaving them stranded. This theory faces timing problems. The void would need to expand rapidly after the galaxies finished forming, before new gas clouds could create younger galaxies nearby. The sequence requires precise coordination that seems unlikely. Others suggest the galaxies formed normally elsewhere, but an unknown force transported them into the void quickly, fast enough to preserve their old stellar populations. But what force moves entire galaxies across cosmic distances without leaving traces? We have no mechanism for that. The final, most disturbing possibility is that these galaxies did not age naturally. Something inside the void accelerated their evolution. A process or field that speeds up time locally, causing stars to live and die faster than normal. The galaxies would appear old because they experienced more time than the universe's actual age allows. This explanation sounds like science fiction. Time does not flow at different rates on cosmic scales. Except it does near massive gravitational fields like black holes. And it does in expanding space affected by dark energy. General relativity permits time dilation under the right conditions. Could the void create those conditions? Could its extreme emptiness warp space-time enough to affect how time passes inside? We have no evidence for this, but we also have no better explanation for why these galaxies look the way they do. And if time flows differently in the void, that might explain the signals we started detecting, patterns that repeat with clockwork precision, as if something inside operates on a different temporal rhythm than the rest of the universe. Something counting down to an event we cannot predict. 3 years ago, astronomers using the Hubble Space Telescope pointed their instruments at one of the 60 void galaxies. They planned a routine observation to measure its stellar populations. Instead, they recorded something nobody expected. The galaxy dimmed. Over the course of 6 hours, its light output dropped by 8%, then slowly recovered to normal brightness. The change occurred smoothly, following a curve that resembled an eclipse, as if something passed in front of the galaxy, blocking our view. The team assumed they caught a random occultation. Maybe a foreground object drifted into the line of sight. They flagged the observation as potentially contaminated and moved on. 2 months later, the same galaxy dimmed again. Same magnitude, same duration, same curve shape. This was not random. This was periodic. The astronomers expanded their survey to include all 60 void galaxies. They set up monitoring programs using multiple telescopes, watching continuously for weeks. What they found sent chills through the astronomy community. 17 of the 60 galaxies showed dimming events, not all at once, not randomly. They follow a pattern. Galaxy A dims, then 3 days later, Galaxy B dims, then 5 days after that, Galaxy C dims. The sequence repeats every 78 days like clockwork, 17 galaxies blinking in a specific order that never varies. No known natural process creates this behavior. Eclipses happen randomly based on orbital mechanics. Variable stars pulse independently of each other. Dust clouds drift through space without coordination. You cannot get 17 galaxies separated by millions of light years to dim in sequence unless something connects them. The dimming itself is unusual. 8% loss of light sounds small, but it requires an enormous object to block that much light from an entire galaxy. We are not talking about a single star being eclipsed. We are talking about the whole galaxy dimming together. The obscuring object would need to be larger than the galaxy itself, spanning hundreds of thousands of light years across. Nothing that large exists in the void. The region is empty by definition. Even if you compressed all 60 galaxies into a single object, it would not be large enough to block 8% of another galaxy's light, unless the obstruction is not a solid object. Some researchers propose we are seeing interference patterns from dark matter waves moving through the void. Dark matter can clump and flow like an invisible ocean. If waves moved through the region in sequence, they might gravitationally lens the background galaxy's light, creating the dimming effect. The theory requires dark matter to behave in ways we have never observed before, forming coordinated waves across millions of light years, maintaining perfect timing for years without dispersing. It is possible, but it stretches our understanding of dark matter to the breaking point. Another hypothesis suggests we are detecting megastructures, artificial constructions built by advanced civilizations. If intelligent beings engineered enormous arrays of objects in specific orbits, they could create periodic dimming events. This explanation appeals to those who search for techno-signatures. The pattern looks artificial, too precise to be natural, but it requires a civilization capable of engineering on scales that dwarf anything in human imagination. Why would they build something that dims galaxies? What purpose does it serve? The most troubling interpretation is that the dimming reveals something moving through the void, an entity or phenomenon that passes in front of galaxies in sequence, temporarily blocking their light. Something so large it eclipses entire galaxies. Something following a path that brings it near each of the 17 affected galaxies in turn. If this is real, we are watching something incomprehensibly massive travel through the emptiest region of space. Something that operates on schedules we can now predict. Something that will complete its current circuit and begin again. The next dimming event is scheduled for 3 days from now. Telescopes around the world are aimed at the target galaxy. Whatever happens, we will be watching, waiting to see if the pattern holds, waiting to understand what casts such enormous shadows, and hoping it never turns its attention toward us. Radio telescopes scan the void constantly now. After the dimming discoveries, astronomers realized they had been ignoring a vast, empty region that might contain unprecedented phenomena. They pointed their instruments at the darkness between the 60 galaxies and listened. The void is not silent. In 2022, the Very Large Array in New Mexico detected radio emissions coming from deep inside the void's interior. Not from any of the 60 galaxies. From the empty space between them. The signal appeared at 1.4 GHz, a frequency often used in radio astronomy because it cuts through cosmic interference cleanly. The emission lasted 43 minutes, then stopped. 2 weeks later, it appeared again. Same location, same frequency, same duration. A pattern emerged over months of observation. The signal broadcasts every 14 days with precision that varies by less than 3 minutes. Radio emissions from empty space make no sense. Radio waves require a source. Stars emit radio waves. Gas clouds emit radio waves. Black holes feeding on matter emit radio waves. But empty vacuum produces nothing. Yet here was a signal originating from a region where our instruments show no matter exists. The signal itself carries structure. It is not random static or simple pulses. The intensity varies in ways that suggest modulation, like someone is encoding information into the broadcast. Teams of scientists ran the signal through every analysis technique they know, searching for patterns that might indicate natural origins or artificial intelligence. Natural pulsars create regular radio signals, but they rotate, causing their beams to sweep past Earth periodically. This signal does not sweep. It appears and disappears without rotation. Rotating radio transients flash randomly, not on perfect 14-day schedules. Magnetars emit radio bursts during stellar quakes, but those events are violent and irregular. This source shows none of those characteristics. It broadcasts calmly on schedule, transmits for 43 minutes, then shuts off completely. The behavior resembles artificial radio stations more than natural cosmic objects. The signal's location presents another mystery. It originates from a point roughly 60 million light-years inside the void, equidistant from 3 of the dimming galaxies. This position forms a geometric relationship with those galaxies. Not random, not coincidental. Specifically placed. When researchers mapped all the dimming galaxies and the radio source together, they found something shocking. The positions form a 3-dimensional lattice, a structure. The galaxies sit at specific points, and the radio source occupies a central node. The whole arrangement spans 100 million light-years, but maintains precise geometric relationships. Natural cosmic structures do not form lattices. Galaxies cluster gravitationally, creating irregular clumps and filaments. They do not arrange themselves in geometric patterns, unless something organized them deliberately. The 14-day broadcast cycle matches exactly 1/3 of the dimming event cycle. While this might be coincidence, the mathematical relationship feels intentional, like the radio source and the dimming events coordinate, like they serve connected purposes. Some researchers propose we are detecting an automated beacon, an ancient transmission left by a long-dead civilization, broadcasting continuously for millions or billions of years, sending a message into the void that nobody has been there to receive. Until now, if true, the beacon's age would be staggering. The void itself is billions of years old, For a signal to broadcast that long requires technology beyond our comprehension, self-repairing mechanisms, power sources that never deplete, engineering that survives the lifetime of stars. Others suggest the signal is not ancient but recent, something new activated inside the void, something that started broadcasting only in the last few years. This timing troubles astronomers because it implies the void's properties are changing now, during the brief instant humans can observe them. What are the odds we evolved intelligence just as the void began revealing its secrets? Either we are incredibly lucky, or the void is responding to something, perhaps to our own radio transmissions leaking into space, perhaps to our gravitational influence as our galaxy moves through space, perhaps to something else entirely. The latest observations show the signal strength increasing. Each 14-day broadcast comes through slightly louder than the last. The growth rate is small, only 2% per cycle, but consistent. Extrapolate forward, and the signal will be 10 times stronger in 5 years. What happens when it reaches full intensity? What is it building toward? We have no answers, only growing concern that we are witnessing the activation phase of something that has been dormant for eons. And then last month, a second radio source appeared. The cosmic microwave background is the oldest light in the universe. It formed 380,000 years after the Big Bang, when space cooled enough for atoms to form. Before that moment, the universe was opaque. Light could not travel freely because it constantly scattered off charged particles. After that moment, light streamed outward, carrying an image of the universe's infancy. We can still see this ancient light today. It reaches us from all directions as faint microwave radiation. The CMB appears almost perfectly uniform across the entire sky, with temperature variations of only 1 part in 100,000. These tiny variations map the density fluctuations that later grew into galaxies and voids. Except in one direction. When astronomers measured the CMB toward the Boötes Void, they found something wrong. The temperature in that region reads lower than surrounding areas. Not by much. Only a few millionths of a degree, but measurable, consistent, real. This temperature drop is called the integrated Sachs-Wolf effect. When CMB light travels through a void, it loses energy. Here is why. As light enters the void, it climbs out of the surrounding matter's gravitational potential. This climb costs energy, cooling the light slightly. As it exits the void on the far side, it falls back into normal space, regaining that energy. Normally, these effects cancel out. Light cools entering the void and warms leaving it. Net change, 0. But the universe expands. Dark energy stretches space while the light crosses the void. If the void grows during the light's transit, the exit point is deeper in the surrounding matter's gravitational field than the entry point was. The light does not regain all the energy it lost. It arrives cooler than it started. This effect is tiny. Most voids create temperature variations of only a few millionths of a degree. The Boötes Void creates a cold spot 10 times larger than expected. The discrepancy suggests the void is expanding much faster than normal voids, or it started much emptier than our models predict. Neither explanation is satisfactory. Faster expansion requires stronger dark energy concentration, but dark energy distributes uniformly. It should not concentrate in specific regions. Starting emptier pushes the problem back to void formation. Why would this region be so much emptier than anywhere else? Some cosmologists propose we are seeing evidence of primordial quantum fluctuations. In the first moments after the Big Bang, quantum uncertainty created slight variations in density. Most of these variations were small. Rarely, a large fluctuation would occur. The Boötes Void might represent an extreme statistical outlier. Calculate the probability and you get numbers like 1 in 10 million. Unlikely, but possible. The universe is huge. Rare events happen somewhere. We might simply be witnessing the tail end of a probability distribution. Except we see other effects that amplify the mystery. The CMB cold spot is not circular. It is elongated, stretched, like something pulled on the void from one direction, distorting its shape. Voids should expand symmetrically in all directions. This one grew asymmetrically. Something influenced its growth pattern. The elongation points toward a specific region of sky. Follow that direction outward, and you pass through the void, through the galaxies beyond it, toward the edge of the observable universe. Does this alignment mean something? Are we seeing a connection between the void and structures too distant to observe directly? Recent simulations suggest another possibility. If our universe is not alone, if parallel universes exist in higher dimensions, collisions between universes might leave scars in space. These collision sites would appear as unusually empty regions. They would stretch the CMB light, passing through them in specific directions. They would violate our standard cosmological models because they formed through processes outside our universe's normal physics. Could the Boötes Void be a scar from a parallel universe collision? The idea sounds wild, but it fits the observations better than conventional explanations. It accounts for the extreme emptiness, the unusual size, the asymmetric shape, and the excessive CMB temperature drop. And if true, it raises a terrifying question. If two universes collided here, are they still in contact? Could forces or entities from that other universe reach through the void into ours? Could the signals we are detecting originate from beyond our reality? The cold spot stares back at us from the cosmic microwave background like an eye, an ancient wound in space that never healed. And now it is starting to open. Light travels in straight lines. That is the basic rule, except it is not quite true. Mass bends space, and light follows the curves. This effect, called gravitational lensing, lets us map dark matter by watching how it distorts background light. When light passes through a void, it should bend very little. Voids contain minimal mass. Without mass, space stays flat. Light continues straight through with barely any deflection. This property makes voids easy to identify. They create blank spots where gravitational lensing vanishes. The Boötes Void does not follow this pattern. Light passing through it bends wrong. Not strongly like it would near a galaxy cluster, subtly wrong. Like the void contains invisible mass that should not be there. Or like space itself has different properties inside the void than outside. Astronomers discovered this anomaly while mapping dark matter distribution. They measure how light from distant background galaxies distorts as it travels through foreground structures. More distortion means more mass along the line of sight. Less distortion means less mass. Simple. When they measured lines of sight passing through the void, they expected minimal distortion. Instead, they found measurable lensing, not as strong as in normal space, but present, consistent, repeatable. The void contains something that bends light even though our instruments show the region is empty. Calculate how much mass you need to produce this lensing, and you get a disturbing answer. The void would need to contain about 10% of the matter that should exist in normal space. Not nothing. Not the expected 1% residual matter in voids. 10%. That is enough matter to form thousands of galaxies. Where is this matter? We cannot see it in visible light. We cannot detect it in radio waves. X-ray observations show nothing. It is invisible across the entire electromagnetic spectrum, yet it gravitationally lenses background light, proving it exists. Dark matter explains part of this. Dark matter does not emit light but does have mass and creates gravitational lensing. Every region of space contains dark matter, even voids. Perhaps the Boötes Void retained more dark matter than typical voids when it evacuated its regular matter. But dark matter and regular matter usually move together. Gravity couples them. When regular matter leaves a void, dark matter follows. Finding dark matter without regular matter requires breaking that coupling somehow. We have no mechanism for that. Another possibility is that we are measuring wrong. Perhaps light bends for reasons unrelated to mass. Modified gravity theories propose that gravity behaves differently on cosmic scales than our current understanding predicts. If those theories are correct, the anomalous lensing might result from altered gravitational laws inside the void. Testing this requires comparing lensing measurements from multiple void regions. Do all large voids show similar anomalies? Or is this unique to the Boötes Void? Preliminary surveys suggest the Boötes Void is unusual. Other voids produce the expected minimal lensing. This one stands alone. The lensing pattern has structure. It is not uniform across the void. Some sightlines through the void show stronger lensing. Others show weaker lensing. Map these variations and you see patterns. Concentrations of whatever is bending the light. The concentrations align with the 60 galaxy positions and the radio source location. Like, there is a network inside the void. invisible filaments connecting the galaxies to each other and to the radio source. These filaments contain enough mass to lens light, but somehow remain invisible to our instruments. What could do that? Regular matter emits light, or at least absorbs and blocks light. Dark matter interacts only through gravity. This hypothetical network must be made of something else. A third type of matter we have not discovered yet, or energy structured in ways we do not understand. The latest gravitational wave detectors might offer clues. If massive objects move through the void, they create ripples in space-time. These ripples propagate outward at light speed as gravitational waves. We could detect them with sufficiently sensitive instruments. Several research groups now monitor the void region for gravitational wave signals. They search for periodic patterns matching the 14-day radio broadcast cycle or the 78-day dimming cycle. Any correlation would prove something massive is moving inside the void, something real enough to warp space-time, something invisible to everything except gravity. They have not found signals yet, but they are improving their sensitivity every month, and they are starting to wonder if whatever is inside the void is moving toward us, or if we are moving toward it as our galaxy drifts through space. Because the lensing anomalies are getting stronger. Year by year, light bends slightly more as it crosses the void. Whatever is in there is growing, or activating, or consolidating its presence, and we still cannot see it coming. Dark matter built the universe. It outweighs regular matter 5 to 1. Without it, galaxies would fly apart. Cosmic structures would never form. The universe we observe could not exist. Dark matter acts through gravity. It clumps around galaxies, holding them together. It forms enormous halos that extend far beyond the visible edges of galaxies. It threads through space in vast filaments, creating the cosmic web. Everywhere we look, we find dark matter. It dominates the mass budget of the cosmos. Except in the Boötes Void, the dark matter is missing. Theoretical predictions say voids should retain about 15 to 20% of their original dark matter content. When regular matter evacuates during void formation, dark matter evacuates too, but not completely. Gravity is not strong enough to clear dark matter out entirely. Some always remains behind. Multiple surveys measured dark matter distribution in the Boötes Void using gravitational lensing and galaxy velocity studies. They found less than 5% of the expected dark matter content. 75% of the dark matter that should be there has vanished. This is impossible, according to standard physics. Dark matter only interacts through gravity. It cannot radiate energy. It cannot push itself away. It cannot escape from a region unless another force ejects it. And we know of no force capable of ejecting dark matter from such an enormous volume. Some physicists propose dark matter self-interacts more than we thought. Maybe dark matter particles occasionally collide with each other, transferring momentum. Given enough time, these rare interactions might clear dark matter from voids more efficiently than gravity alone. Models testing this idea show it cannot work fast enough. Self-interactions strong enough to clear the void completely would create other observable effects we do not see. The hypothesis fails. Others suggest the void formed differently than normal voids. Perhaps it began with much less dark matter than average. A primordial underdensity that has persisted since the Big Bang. This requires fine-tuning initial conditions to an extreme degree. Possible but statistically unlikely to the point of absurdity. The third option is that something removed the dark matter after the void formed. Something came through this region and swept it clean. But what has the power to affect dark matter on such scales? Dark matter barely interacts with anything. It passes through regular matter like ghosts. Moving it requires forces we do not have access to. Unless the void connects to something beyond our space-time. If higher dimensions exist, dark matter might be able to leak into them under certain conditions. The void's extreme emptiness might create a weakness in the dimensional barrier. Dark matter could drain away into other universes, leaving our space depleted. This sounds like speculation from theoretical physics, and it is, but the observations demand explanations outside standard physics. We have to consider possibilities we normally dismiss. The distribution of the remaining dark matter is equally strange. Instead of spreading uniformly across the void, it concentrates in specific locations. The same locations where we detect anomalous gravitational lensing. The same locations aligned with the 60 galaxies and the radio source. Like something is collecting the dark matter, gathering it from the emptiness and storing it in particular spots, using it for purposes we cannot fathom. Recent computer simulations tried to model what would happen if you removed most dark matter from a cosmic void. The results were dramatic. Without dark matter's gravitational scaffolding, the remaining regular matter becomes unstable. Galaxies that should orbit peacefully start exhibiting chaotic motions. The void structure should collapse or fly apart. Yet, the Boötes Void remains stable. The 60 galaxies maintain their positions. The geometric lattice persists, despite lacking the dark matter foundation that should support it. Something else is providing stability. Something replacing dark matter's gravitational role. A few researchers dare to suggest the void is not empty. It is filled with something we cannot detect yet. A type of matter or energy that interacts with normal and dark matter gravitationally, but remains invisible to all our current instruments. This hypothetical substance would need to be even more weakly interacting than dark matter. A shadow of a shadow. Call it dark matter or phantom energy. The name does not matter. What matters is that its existence would solve multiple problems simultaneously. It could explain the missing dark matter, the anomalous lensing, the stable galaxy positions, and the geometric structures we observe. But it also implies the void is not empty at all. It is full, brimming with an ocean of something we are only beginning to perceive. And that ocean is starting to stir. We can sense its currents now, the changing lensing patterns, the shifting gravity fields, like a vast entity waking from an eon-long sleep, like something ancient, noticing our observations and deciding to respond. The question is no longer what happened to the dark matter. The question is what took it, and whether it plans to take more. The void has boundaries, sharp ones. On one side, galaxies crowd together in walls and filaments, glowing with the light of billions of stars. On the other side, emptiness. The transition happens abruptly, over distances of only 10 to 20 million light-years, a cosmic cliff where the universe falls into nothing. These boundary regions should follow predictable physics. Galaxies near the edge feel gravitational forces from two directions. The wall of galaxies behind them pulls backward. The empty void ahead provides minimal forward pull. Net result, galaxies should slowly drift toward the walls, moving away from the void. The void should shrink over time as galaxies crowd inward. That is not happening. The boundary galaxies are not moving toward the walls. Some are not moving at all. Others are moving toward the void, backward, into the emptiness. Astronomers discovered this by measuring galaxy redshifts. Redshift tells us how fast a galaxy moves toward or away from Earth. Compare many galaxies in a region, and you can map their collective motion. Most cosmic structures show galaxies falling toward higher density regions due to gravity. The void edge shows the opposite, galaxies falling toward lower density, toward emptiness. This violates fundamental physics. Unless something inside the void is pulling them inward, calculate the gravitational force needed to reverse galaxy motion, and you find it requires enormous mass. More mass than the 60 void galaxies contain. More mass than any structure we can detect. An invisible mass concentration lurking in the void's interior, massive enough to overcome the gravitational pull of surrounding galaxy walls. Where is this mass? What is it made of? We have no answers. Dark matter could provide the mass, but we already established the void contains less dark matter than normal, not more. Regular matter is visible, and we see almost none. Some unknown form of matter would need to fill the void, a lot of it. The gravitational anomalies are not uniform around the void's edge. They are strongest in 3 locations. These locations form an equilateral triangle when viewed from Earth. The triangle's center coincides with the radio source position. The 3 vertices align with 3 of the dimming galaxies. Geometry again. Patterns suggesting organization rather than natural randomness. Astronomers hate finding geometry in nature because it implies either incredible coincidence or deliberate construction. Neither option is comfortable. Monitoring stations now track the motion of edge galaxies continuously. They measure position changes year by year. The data show acceleration. Galaxies are not just drifting toward the void, they are speeding up. Whatever force pulls them is getting stronger over time. Extrapolate the acceleration curves forward, and several edge galaxies will cross into the void within the next million years. Once inside, they will become part of the geometric lattice. They will join the 60 existing galaxies in whatever pattern or network spans the interior. Is the void feeding, growing, collecting matter from its surroundings? Voids typically expand by pushing matter away. This one appears to be pulling matter inward, exactly backward from expected behavior. Some theorists propose we are witnessing the formation of a structure called a cosmic string. Cosmic strings are hypothetical defects in space-time left over from the Big Bang. They have enormous gravitational influence, despite being thinner than atoms. A cosmic string passing through the void could create the gravitational anomalies we observe. The problem with this theory is that cosmic strings should be visible through their gravitational lensing. They bend light from background objects in distinctive ways. Multiple surveys searched for cosmic string signatures in the void region. They found nothing. If a string exists there, it is hiding somehow. Another proposal suggests the anomalies result from frame dragging. Einstein's general relativity predicts that rotating mass drags space-time around with it. Usually, this effect is tiny, measurable only near rapidly spinning black holes. But if something enormous was rotating inside the void, it might drag space on much larger scales. What could possibly rotate inside an empty void? Nothing natural. No known cosmic structure rotates coherently across hundreds of millions of light years. Such rotation would require coordination, purpose, engineering. The most recent observations come from gravity wave detectors. These instruments measure ripples in space-time caused by accelerating mass. They have not detected any waves from the void yet, but they have found something equally strange. The gravity wave detectors show noise when pointed at the void, not random noise, structured noise, a low-frequency hum that persists beneath the detection threshold. It is too weak to confirm as a signal, but it is always there, always at the same frequency, always coming from the same direction. Engineers think it might be instrumental error, except every detector shows the same noise pattern. Detectors in Louisiana, Washington, Italy, Japan, all of them pick up the hum when aimed at the void. Coincidence seems unlikely. Could this be the sound of space-time itself resonating? Like the void is a cavity that amplifies certain gravitational frequencies? Or are we detecting something's heartbeat? A massive object pulsing in the darkness, too slowly for us to notice, but constant enough to create perpetual vibrations in the fabric of reality. The hum frequency corresponds to a period of about 2 years. If it is real, if something truly pulses with that rhythm, we have been detecting it for 3 cycles now. 3 repetitions of whatever process generates the signal. The next peak is calculated to occur in 9 months. Every gravitational wave detector on Earth will focus on the void when that moment arrives. Either they will confirm the signal exists, or they will prove it is an artifact and we can stop worrying. But deep down, the researchers already know what they will find. The hum is real, the void is speaking to us, and soon we will understand its message. The Big Bang was not smooth. The earliest moments of cosmic history were violent, chaotic, transformative. Space inflated faster than light, quantum fluctuations magnified to cosmic scales. Phase transitions ripped through reality as fundamental forces separated from their unified origin. Some cosmologists believe these phase transitions left scars, places where the fabric of space-time tore and never quite healed properly. Cosmic wounds that persist as unusual structures we observe today. Voids might be these scars, regions where the phase transition happened incorrectly, creating zones of underdensity that grew into the empty spaces we map now. Most voids would be minor defects, small tears that barely affect cosmic evolution. But occasionally, a major rupture would occur, a wound deep enough to create something like the Boötes Void. This theory predicts several things we can test. First, cosmic wound voids should have unusual shapes. Natural voids form symmetrically. Wounded voids would follow the geometry of the original tear. We should see elongation, asymmetry, or other geometric irregularities. The Boötes Void is asymmetric. Its elongated shape aligns with the theory's predictions. Check. Second, cosmic wounds should affect the cosmic microwave background in specific ways. The temperature variations should show patterns related to the defect's structure, The cold spot should have features beyond simple cooling. The CMB cold spot associated with the Boötes Void has precisely these features. It shows structure within structure, sub-patterns that do not appear in normal voids. Check. Third, if voids are wounds, they should still be bleeding, slowly leaking energy or particles into the surrounding space. We would detect anomalous radiation near the void's edges, excess heat or unusual particle distributions. Infrared surveys of the void's boundary regions show slightly elevated temperatures compared to other void edges, not by much, only a few degrees, but measurable and consistent. Check. The theory is holding up, but it makes one more prediction, the most important one. If voids are wounds from the early universe, they should contain relics, remnants of the conditions that existed during the Big Bang. These relics would be exotic, objects or fields that cannot form in today's universe. They would represent physics from an era when the cosmos operated under different rules. Finding such relics would revolutionize physics. They would give us direct evidence about the universe's first moments. They would test our theories of cosmic inflation and phase transitions. They might reveal new fundamental forces or particles. Could the signals from the Boötes Void be these relics? Could the radio broadcasts and dimming events represent ancient physics still active inside a cosmic wound? The timing matches. The wound formed 13 billion years ago. The relics would have been trapped inside since then. We are only now developing instruments sensitive enough to detect their activity. Some researchers go further. They propose the void is not just leaking energy, it is leaking structure, information. The geometric lattice we observe might be an imprint of higher dimensional physics bleeding through the wound, like looking at a shadow cast from a reality we cannot directly perceive. If true, we are witnessing something beyond our universe's normal physics, a window into the higher dimensional space that contains our cosmos, or into the quantum foam that underlies space-time, or into the symmetry-breaking events that occurred during cosmic inflation. Any of these possibilities rewrites textbooks. They elevate the void from an astronomical curiosity to a fundamental physics laboratory, a natural experiment that reveals how the universe actually works at its deepest levels. But there is a darker interpretation. Wounds can become infected. If the void is a tear in reality, something from outside might have entered through it. The signals we detect might not be remnants of the Big Bang. They might be evidence of intrusion, of something from another universe or another dimension, using the wound as an entrance point. This explanation fits the observations uncomfortably well. It accounts for why the void seems more active now than in the past. The wound is widening. The intrusion is growing. What started as a small defect billions of years ago has expanded into an invasion route. We might be watching the early stages of a cross-dimensional incursion. The radio signals could be communication between the intruding entities. The dimming events could be their construction projects. The gravitational anomalies could be their machinery altering local space-time. Most scientists dismiss this interpretation as science fiction, but a few take it seriously. They point out that we have no experience with cosmic wounds or higher dimensions. Our intuition about what is possible or impossible does not apply. We should consider all explanations that fit the data, no matter how uncomfortable they make us. The difference between a remnant and an intruder is intent. Remnants are passive. They exist but do nothing. Intruders are active. They expand. They build. They change their environment to suit their needs. The Boötes Void is doing all those things, changing, expanding, building geometric structures, becoming more active year by year. That is the behavior of an intruder, not a remnant. And if something is invading through the void, we need to know what it wants, why it is organizing matter into lattices, why it is broadcasting signals, why it is collecting galaxies. We need to know before it finishes whatever it is building, because the construction appears to be nearing completion. The geometric patterns are almost perfect now. A few more galaxies falling into place. A few more years of radio broadcasts. Then the structure will be complete. And then what? What happens when an invading force from beyond our reality finishes its construction inside a cosmic wound? What capability does that give them? What can they do that they could not do before? We are about to find out. The countdown has begun. The structure will be complete within a decade. maybe sooner, and we will learn whether we discovered a fascinating astronomical phenomenon or a threat to our continued existence. Voids grow over time. Dark energy pushes their boundaries outward, evacuating more matter and creating larger empty regions. This expansion happens slowly. Voids increase in size by about 1% every billion years. Measure a void size now, come back in 100 million years, and you will barely notice the difference. The Boötes Void is growing faster, much faster. Analysis of historical astronomical data shows the void's diameter increased by nearly 2% in just the last 50 years. That is 10,000 times faster than predictions allow. How do we know? Astronomers measure void sizes by mapping the galaxy distribution around them. Find where galaxies stop appearing, and you have found the void's edge. Compare maps from different years, and you can track expansion. Early surveys from the 1980s placed the void's diameter at 320 million light-years. Modern surveys put it at 330 million light-years. 10 million light-years of growth in 40-something years of human observation. This should be impossible. Void expansion depends on dark energy's strength, which is constant throughout space and time. You cannot suddenly accelerate a void's growth without changing dark energy's properties. And if dark energy changed properties, we would detect that change everywhere, not just in one void. Yet the Boötes Void expands abnormally. Something is pushing its boundaries outward faster than dark energy alone can account for. Something local to the void is driving accelerated expansion. The expansion is not uniform. Different edges of the void grow at different rates. The side facing toward the radio source location expands fastest. The opposite side expands slowest. The void stretches in a specific direction, becoming more elongated each year. This directional growth implies a force gradient. Something inside the void pushes harder in one direction than others, like a pressure wave propagating outward from a central point, or like an explosion expanding through space. Except normal explosions slow down over time as they lose energy. This expansion is accelerating. Year by year, the growth rate increases. The void expands faster now than it did a decade ago. Extrapolate forward and the expansion rate will be even higher 10 years from now. At current acceleration rates, the void will double in size within 2 million years. That is nothing on cosmic timescales. An eye blink. Structures that usually take billions of years to evolve will undergo dramatic changes in an instant. What happens to the 60 galaxies inside when the void doubles? Do they spread apart, maintaining their geometric pattern but on a larger scale? Or does the expansion crush them, forcing them closer together until they collide? Computer simulations suggest neither outcome is stable. The galaxies should either fly apart completely or merge into a single massive structure. Both processes would take hundreds of millions of years normally. But if the void expands as fast as observed, these events could happen in only a few million years. We might be watching a cosmic collision in extreme slow motion. Slow from our perspective, but incredibly fast by astronomical standards. The 60 galaxies, arranged in their geometric lattice, might be falling toward a common center. In a million years, they will meet, and when they do, the energy release would be visible across the observable universe. Unless something prevents the collision, unless the geometric arrangement is not random positioning but a carefully balanced structure, like balls on a pool table placed in specific spots where the table's curvature keeps them stationary. The void's expansion might create a space-time geometry that holds galaxies in place despite the forces trying to move them. This would require exotic physics. Space-time curvature strong enough to balance galaxy motion exceeds what normal matter can produce. You would need immense gravitational fields, black holes, or something even denser. Recent observations found another clue. Stars at the edges of the 60 void galaxies show unusual velocities. They orbit their galaxy centers faster than expected based on visible matter. This is the classic dark matter signature.